I'll get going, pitching mostly to the YouTube audience, which I'm sure are massing in their thousands. So I was asked to give a kind of general talk about Arctic sea ice, which some of you will know about and some of you will not. Just to give a kind of update on the situation, but then give maybe a slightly like intermediate level hint at some of the processes that are going on. But my clicker doesn't work, so we might have to. There we go. But I thought I'd start with like a non-sea ice related slide. So this is my favorite slide from the whole IPCC assessment report, and it basically tells us that in terms of global warming, all of this talk of like representative concentration pathways and shared socio-economic pathways are actually just not very important at all. And the total global warming that we experience just scales linearly with the amount of carbon dioxide that goes into the atmosphere. So we can fuss around about when we put it in and how quickly we put it in, but essentially the relationship between carbon dioxide and global warming is linear and predictable and consistent. So good to get that out of the way. But my clicker is unfortunately not working. Okay. But obviously this talk is about the Arctic and it's about sea ice. So I made a map of all of the areas of the Earth that have exceeded 1.5 degrees at any given point in time relative to a mid-century baseline. And you can see that these hotspots are really increasingly prevalent over the Arctic. So the Arctic, almost as an entirety, has passed 1.5 degrees above even just a mid-century baseline, let alone the IPCC baseline, which is about 50 years before that. You can also see a lot of warming around Antarctica. There's some question about the baseline in those areas. So we don't have a very rigorous pre-industrial baseline in Antarctica. So I would encourage you to draw your eyes towards the middle of the map, which is where the Arctic is positioned, and reflect on the extraordinary heat that is currently going on in the Arctic, but actually has been for the last decade or so. Next slide. That's okay. I think it's the animations. So here's a zoomed in map of the last year's temperatures in Antarctica from November of last year to October of this year. And you can see that parts of the Arctic have warmed by easily in excess of 4 degrees and going up towards 6 degrees in the Svalbard archipelago, just to the right of Greenland, to the east of Greenland, the geographer might say. So it really has seen exceptional warming relative to the global average, which this year is probably about 1.5 degrees. So just symbolically tipping over the Paris threshold, even though the long-term average probably isn't there yet. But the Arctic's long-term average temperature rise is well in excess of 1.5 degrees. We're talking in excess of 2, in excess of 3, maybe approaching 4, but we'll get to that in the next slide. Next slide, please. Here's a map of that warming by latitude. So you can see in the gray shaded area, the warming in the Arctic Circle is really quite exceptional and increases as you go towards the pole, exceeding 3 degrees and approaching 4 at the North Pole. Next slide. And here's what I mean about the warming relative to the global average. Over time, it's just crept above higher and higher. So in this data set, the global average temperature this year is approaching 1.5 degrees. But in the poles, so north of 66 degrees, we're in excess of 2.5 degrees of warming. And in fact, in some years, we've seen in excess of 3.5 degrees of warming. Next slide, please. Oh, yeah, that is the next slide. Okay. It's quite notable that in winter, so if we just look at the meteorological season of December, January, and February, the warming in the Arctic is in excess of 3 degrees, and this year will likely be in excess of 4 degrees. So in winter, the world is warming slightly faster, but the Arctic is warming exceptionally faster. It's the season of greatest warming for feedbacks that I'll get into later. Next slide. Here's an animated map of what you've just seen that really drives home those winter rises. So in the 70s, not a lot going on. It took a while for Arctic amplification to really kick off. But then you'll see as the years tick by in the 2010s and up to 2024, you see a really pronounced seasonal distribution of Arctic warming. In the darkest months, it's basically the greatest, which I think is somewhat counterintuitive when you think about this ice albedo effect, because it's when the ice albedo effect is completely missing in the winter, there's no sunlight at all. That's when we see the strongest amplified warming. Next slide. I'll just talk for a minute about what's causing that, because I think it goes missing in a lot of the COP discussions that we have. So here is basically a summary of these Arctic amplification feedbacks. And you can see the albedo effect, surface albedo, labeled by A. And you can see that because it's higher than this diagonal line, it amplifies Arctic warming relative to the points below the diagonal line, which amplified tropical warming. But the A dot that you can see there is just one among quite a few different feedbacks. So it turns out that just northerly latitudes, the way that the feedback of the Earth's radiation works, particularly in winter, this is called the Planck curvature effect, is just as strong as the albedo effect in terms of partitioning warming between the Arctic and the tropics. But we also have this LR thing, this dot here, which is way out from that center line of tropical versus Arctic amplification. That's the lapse rate feedback. So changes to the lower structure of the atmosphere that mean that warming basically gets trapped at the surface and can't be distributed about the atmosphere, where it can then be lost into space. So there's a whole bunch of physics going on. We also have Arctic heat transport in pink, where heat just gets moved up from lower latitudes into the Arctic by weather systems, essentially. So these four contributing factors that cause the Arctic to, at least historically, have warmed by 4 times the global rate in the last 40 years. We did some work on this. So my time at the Cryosphere Pavilion a couple of years ago in Egypt, I was asked a direct question about how much has Arctic amplification actually contributed to global warming? Like, how quickly will we cross the Paris Agreement in a world without Arctic amplification versus one with? And with a PhD student in my group, much more talented than I am, we worked it out. So we looked at the climate models, we looked at the forecast for when we're going to breach the Paris Agreement under low and moderate emission scenarios. And we worked out that we'll cross the 1.5 degree boundary about 5 years earlier, just because of Arctic amplification, than we otherwise would. And we'll cross the 2 degree limit of the Paris Agreement 8 years earlier than we otherwise would, just because of amplified warming in the Arctic. So we didn't consider amplified warming in Antarctica at all. We just thought about a world where the Arctic warmed at the global average rate. And yeah, this is the finding, 5 to 8 years faster, depending on the model that you look at. Next slide, please. So some key points about Arctic amplification before I move on to the ocean. So Arctic amplification contributed 10% of global mean temperature rise, despite occupying quite a small fraction of the Earth's surface, only 4%. So it's an outsized contributor to our breaches of these Paris targets. 5 and 8 years earlier, as I just said. Another interesting finding from this study was that variability in near-term Arctic warming contributes 15% of the model uncertainty. So our uncertainty in when we breach these Paris limits is dominated by uncertainty just in Arctic warming. And that's kind of strange, because the Arctic is one of the most poorly observed places in the world, arguably the most poorly observed place in the world outside Antarctica. So we've got this really, really uncertain part of the Earth system that's also really, really poorly observed. And I find that quite striking. Okay, so that's the rapid warming of the atmosphere in the Arctic cleared up. The second bit of the world that you need to understand before you think about sea ice decline is the ocean. So the sea ice is being assaulted basically by warm temperatures from the air, but also warm temperatures from below. And this is a map of the ways and the paths through which warm water from the Atlantic is seeping into the Arctic, particularly the European sector of the Arctic. So some of it's coming up west of Svalbard through this part called the Fram Strait, but we also see really pernicious sort of tentacles of warm, salty Atlantic water sneaking up into the Arctic through the Barents Sea, so north of Norway and western Siberia. Next slide, please. I'm going to try and limit the level of complexity slightly while getting the key facts in. So the Arctic has this characteristic layered structure. It's like a cake. and it has different what we call water masses with very distinct physical properties just stacked on top of each other. And kind of surprisingly, when you first hear about it, they don't actually mix very well. So right at the top, mostly due to river input, we have a very, very fresh cap. And that fresh cap is actually very cold. And normally you're used to cold water sinking below the warm water. But the Arctic is almost unique in the world because this layered structure of the cake is stratified by salinity and not temperature. So we somehow have this situation where we have colder water above water warmer in the Arctic. And that's actually quite a precarious situation. But it's basically by dint of sea ice transport, but the unusually large amount of fresh water input by the rivers. Right below that top layer of the cake, we have a rapid increase in salinity, but the temperature doesn't change very much. So you can think of the cold water cap like a piece of sponge, and then under that we have this icing, this glue, that glues together two otherwise quite disparate layers. So we call that the halocline. And when you go down through the halocline, basically the water just gets a lot saltier very, very quickly. And you can actually see it if you drive a submarine under the water. It's sometimes actually visible, this layer of water where it just gets denser and denser very, very rapidly. That halocline, this glue of the icing, overlies this dangerous layer of Atlantic warm, salty water. And the only real reason that Atlantic water is sitting below the icing is because it's salty and it's heavy. But what we're tending to see due to this pernicious infiltration of Atlantic water is this salty water is messing around with the halocline. It's thinning the layer of icing, but it's also weakening the layer of icing. And we're seeing Atlantic water starting to mix upwards into this cap, into this freshwater cap, where it then interferes with the sea ice. And we can actually detect this in satellite measurements of the sea ice. So if we can correct for various factors, and we can begin to assess the actual level that this halocline penetration, this weakening of this cap, is actually affecting the sea ice. And we can see that thermodynamic growth alone in the sea ice in the Barents Sea, this European sector, is beginning to decline. So as well as being hit from above, the sea ice is also being hit from below by the water. It's this double threat to sea ice growth that we've come to see in the 21st century. Next slide. So let's actually get to the sea ice, right? Here is a satellite image constructed from lots of microwave measurements, so radio spectrum measurements of sea ice in 1980 and 2024. And this is the sea ice in March, so it's close to its maximum extent. It might look quite similar, but there are a couple of key features I want to draw your attention to. So we've seen, even in the maximum extent, a decrease from the southerly latitudes of down by North America and Canada, the bottom. But we've also seen a loss of this lobe of sea ice sticking out east of Greenland. So we've seen decreases in the maximum extent, but we've also seen much more radical, actually, decreases in the minimum extent. So next slide. Here's the change in the minimum extent since satellite measurements really began in earnest in the 1980s, relative to the September we've just had. So I don't need to explain to you in such detail the differences you can see in these two images, because it's very striking. The sea ice has retreated away from the North Siberian coast, but it's also retreated away from the north coast of Alaska into this core of more robust, healthier, if you will, thicker, rougher, multi-year ice in the middle of the Arctic. It's colder there, the ice is better protected, but things are changing. So we can perhaps more rigorously look at this as a graph over time. Next slide. Here's how the maximum extent has changed. I think this graph gets forgotten a lot, actually. We tend to focus on the minimum extent and how that's changing. It's very symbolic. It makes the New York Times every year. We get press releases from the National Snow and Ice Database. But the maximum extent is actually showing a superlinear decline with climate change. It's one of the most robust indicators of climate change to date, and I think it deserves a bit more credit. But we should turn to that minimum extent. The headline figure that everyone talks about, a bit noisier, actually, a bit perhaps less linear, a bit less striking, but certainly nonetheless shocking when you consider it. I did a bit of analysis yesterday. If you could just click on one slide, there's a kind of narrative developing that we haven't seen any change in the minimum extent over the last like 18, 19, 20 years. But I did a bunch of like regressions. I drew this blue line in a scientific way, in basically every way I could up to the present day. and I was not able to make it flat. So there's no time window that you can pick where it does actually flatten out or even become positive. It is consistently a negative line. Basically, if you just take any time period to today. So I just wanted to debunk that myth out of the gate there. Next slide. So one tricky thing that it's come out recently that this flattening, if you could call it a flattening because it's not actually flat, is potentially due to quite a recently discovered mechanism of Antarctic sea ice called the Arctic dipole. And some people refer to it as the Arctic switchgear mechanism. And it turns out we've been in a positive phase of this atmospheric circulation pattern for the last 15 years, which may have been buffering the rate of sea ice loss. And this is a relatively recent development in the last couple of years. But interestingly, this 15-year pattern, it's nearly up. In fact, it is up. And there's the potential that a switchgear mechanism that almost defends Arctic sea ice against loss is about to switch back. We're near the end of the cycle. So there is the real potential that we're going to see another significant drop in the minimum extent in the next 5-year period. So I would not take this leveling out as a symptom of a broader flattening of the curve. Another interesting thing is that the way this next drop-off might happen is an increase in Atlantification. So as well as an atmospheric circulation pattern, there's a very real ocean component that is rapidly becoming better understood. Next slide, please. I also wanted to raise the prospect that there's more to sea ice than just where it is. And there's more to sea ice than the time series of this minimum extent and even the maximum extent. Here's a map of the ice age. So these pixels are marked based on whether they contain ice of a given age or not. So the red ice, the red pixels are pixels that contain ice that's 5 years or more old. And the dark blue is seasonal ice, so ice that's just 1 year old. And what you'll obviously notice is that the red on the left is very dominant and then is almost completely absent in the present day. So we've lost almost entirely this unique environment of old, rugged 5-year-old ice. So we've already seen a profound shift, a threshold that's already been crossed, and that we've lost the multi-year ice cover, the old ice cover of the Arctic. So we think a lot about future projections of climate change, but in many ways, Arctic climate change has already happened, and we've seen an extinction event of this old ice. Next slide. Here's a graph of how that happened, because I only showed you the picture of the 1980s and the picture now. It turns out that old ice kind of just fell out of the Arctic, actually. It didn't really melt away in the Arctic. It was suddenly just dropped out in these two stepwise events, we call them. One in around 1990 and the other in about 2007. And I think this really showcases the vulnerability of sea ice to the wind. So it's basically a wind pattern that drove these two events, and we just lost it in a flash. So sometimes sea ice decline is linear when we think about it as an aerial decline, a decline in the spatial coverage, but sometimes it's quite almost violent and abrupt. So when we're thinking about tipping points in the Earth system more broadly, I often reflect on this graph because there were two quite abrupt tipping points in the Arctic system that nobody could really forecast, right? You could never have run a forecast and seen these stepwise reductions appear. And I think that is something to bear in mind in terms of the precautionary principle, that our ability to forecast Arctic sea ice, but also many of these cryospheric systems is quite poor. So sometimes things are linear, sometimes they're abrupt. Next slide, please. As well as the age of the ice, in fact, personally, I think a lot about sea ice thickness and the way that sea ice thickness has changed over the years. So sea ice area has shrunk by approximately a factor of 2, and that's actually also true for the sea ice thickness. Here's one study that was very high profile last year in Nature, where they examined the thickness of ice passing through the Fram Strait, where the ice just fell out in 2007. And they saw a really, again, that stepwise reduction in not just ice age, but sea ice thickness. So on the right, you can see a histogram, a distribution of the thicknesses in the Arctic. And early on in the Arctic's observational history, we saw that blue broad peak of thickness just under 3 meters. But then the later period is characterized by thicknesses below 2 meters. So we saw quite an abrupt shift in the sea ice thickness of ice that was being exported out of this gate. Next slide, please. You might say, oh, well, this is like an observational bias, right? You're looking at sea ice that falls out of this little gap between Svalbard and Greenland. And they made some good arguments against that in the paper. But I have another argument based on my own research where we have satellite estimates of sea ice thickness at all these, what we refer to as marginal seas. And in the marginal seas, we see quite a lot of noise, but also a very clear pattern of reductions in sea ice thickness that are butted up against the Alaskan shelf, but also right along the Siberian shelf, an area of the Arctic that we call the Northeast Passage or the Northern Sea Route, right in the middle. And that has quite profound effects on the environment and the ecology, but it also has profound effects on the economy and our human society, because on the next slide, you can see how productive this sea route is in this area of sea ice thinning for ships. So this is an extremely lucrative way to ship a car from China to Europe, or extract resources from the shelf seas, or move liquid natural gas from LNG ports on the northern coast of Siberia. So the fact that the sea ice is thinning is a disruption to the environment, but it's also an opportunity for people who may seek to exploit the environment. So I think that's very important to bear in mind. This red route just symbolizes the alternative proposition, right? For how far you have to sail to move that car or to move that cargo from Europe to China if you were to avoid the Arctic Sea route. Next slide. We can also think about the future. So we make model projections for the Arctic. And here is an example of even how sensitive the Arctic is to the difference in the emissions just in a low emission scenario and a very low emission scenario. So you can see only by keeping emissions very low, by making radical cuts in the immediate near term, that's the only way that we can save the sea ice in September and October, right? So hopefully you can see where the sea ice is in white. This is in 2100 at the end of the century. And in September and October, even in a low emissions pathway, RCP 2.6, we basically lose the summer sea ice. So it's only by sticking to a very low emissions pathway, 1.9 watts per square meter of radiative forcing by the end of the century, that we can keep September Arctic sea ice there, keep year-round shade in the Arctic Ocean. Next slide. Here is that expressed as a line graph. Sea ice scientists are often quite keen to say that 1 million square kilometers in the Arctic is a practically ice-free scenario. But actually, and the justification for that is kind of historical, that we thought that ice would persist in crevices, nooks, crannies, fjords, well through the end of the century. But the models make clear that you can actually destroy all of the Arctic sea ice under medium and high emission scenarios. And the meaningfulness of this practically ice-free threshold of 1 million square kilometers doesn't actually persist in the models. So it is quite easy to just wipe out all Arctic sea ice in models under medium and high emission scenarios. Actually, even in winter under this very high emission scenario of RCP 8.5 or SSP 8.5 as we now call it. So that is basically all of the science I wanted to present in this talk. But I think I just have one more slide of how cool sea ice is. And I do like to just say that because it's easy to get carried away with graphs and plots and maps and figures. But sea ice is actually just an amazing thing. Sea ice is this beautiful environment that you can travel for miles and miles over the ocean. The ice here was about 30 centimeters thick when we went skiing for the day in Antarctica. And it's just a part of the environment that we're losing at a profound and shocking rate. And I love it, but I tell you what, people that rely on it for hunting and culture and living every day of the year, indigenous people in the Arctic, they love it more. And we can talk about the ecological disruption, we can talk about the economic influence of sea ice decline, but actually people that use the sea ice are super vulnerable. People that have it as part of their culture are super vulnerable to it too. So it's worth considering sea ice finally as a cultural object that's being lost, particularly this old sea ice. So we've already lost old sea ice, and I think it will be such a crime against humanity to lose sea ice in the summer completely, even the thin stuff. So that's the image I wanted to close on. Thank you for coming. Cool. If anyone wants to ask you a question, please go ahead. Yeah. Yeah. So there's no direct effect of sea ice melting on sea level rise, although it actually does control some of the oceanography in Antarctica, particularly. So there is a small indirect effect from a freshwater. It basically affects the freshwater balance of the ocean and has a small indirect effect that way. But also, when sea ice retreats around Antarctica, it makes the ice shelves and ice sheets in Antarctica much more vulnerable to melting. And that is a very significant, that is in fact the dominant influence on sea level rise. So the loss of sea ice in Antarctica is really making ice shelf melting much worse, and that is impacting sea levels. Ecologically, it's quite profound as well because it's a shading element of the Arctic Ocean, particularly in the summer. So it keeps the sea ice, it keeps the upper ocean dark. It suppresses primary productivity. This shading influence, probably. Jacqueline might be upset with me for saying that. A biogeochemist. But certainly, regardless of the net effect on like biomass production, the sea ice retreat is undoubtedly introducing invasive species in the Arctic. So subarctic animals are moving up. It's sometimes called the escalator effect or the elevator effect. They move up and they displace Arctic animals. This disruption to fisheries, but also obviously there's charismatic megafauna like whales, polar bears. In Antarctica, we saw penguins really suffer from the 2023 sea ice conditions. So there's a lot going on ecologically at basically every level in the food chain. I would also just say by interfering with the physical oceanography, we're also potentially influencing Atlantic overturning in the northern hemisphere, but then our ability to take carbon dioxide out of the atmosphere and sink it to great depths in the southern hemisphere. So in both hemispheres, there's real disruption to ocean circulation, which could have quite profound long-term consequences that we can't necessarily go back from. So there's a lot going on with sea ice decline. Yeah. So the question for the microphone was, what caused the stepwise reduction in multi-year ice extent? Basically, it's atmospheric circulation. It turns out. So shifts in the wind pattern that alter this, what we call the transpolar drift, that transports ice from Siberia to the gap between Greenland and Svalbard, and that's quite poorly understood what drives that actually. So although we can document it, we have a poor understanding of what drives it. A lot of smart people, much smarter than me, are working on that right now. Yeah. 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 Could you go back a slide? Just one? Possibly two. Oh yeah, no, this is good. So the way to like decipher the modeling stuff that you've just indicated is we have these shared socioeconomic pathways, and the total amount of radiative forcing, which is like how much energy hits the Earth, is the last number. So 2.6, 4.5, 7.0. The number before that is a much more cryptic number, and it really gets in the way of investigating what you're talking about. So that actually really refers to the scenario that produces the radiative forcing at the end. And it's very, very inconsistent between model experiments, model runs, the things that get submitted to the CMIP6. And to get to the point, it's very uncertain, particularly the aerosol, even the evolution of aerosols into the 21st century. We really don't know how that's going to play out. Like, we don't know. We can have scenarios for reducing greenhouse gas emissions, but quite how those correspond to scenarios of aerosol emissions is unclear. So a lot more work needs to be done on that. I mean, just from first principles, right? The reduction in albedo over sea ice. In many ways, the damage has already been done because the black carbon that does the most damage is the black carbon that settles on that persistent multi-year ice that's already been lost. So we've kind of, from the sea ice perspective, we've blown it from black carbon, but there is a really significant effect on terrestrial snow cover and particularly Greenland. So the Greenland ice sheet, profoundly affected by black carbon. So it's definitely something we need to deal with. Yeah, it's a significant issue. I wish I could be more specific, but we're constrained by the modeling scenarios. Yeah. Yeah. It's more resilient to melting. So it's thicker. It's often covered in better snow that's more reflective to sunlight. It's also slightly fresher, actually, which influences the temperature at which it melts. By fresher, I mean less salty. It's a terrible bit of like scientific jargon. So there are several reasons why multi-year ice is much more robust to melting, but it also provides more effective shade. So the thinner first year sea ice is more easily penetrated by light, partially also to do with the difference in the snow cover regime on multi-year ice. So it's geophysically quite distinct, and it's a shame we've lost it, actually, because it was doing a big system service for us. It was providing a lot of benefits. Yeah. Cool. Sounds like we're done. Thanks for coming, everyone.